Hello everyone. In this video, we will begin to examine topic 5, electricity and magnetism. And in particular, we will focus in on electric fields and our initial understanding of the concept of electric charge. So, in electricity and magnetism and electric fields, there are a set of sort of traditional pretty easy to perform practical experiments that led to the model of electric charge, which of course you are all already partially familiar with. I really would encourage you that if you haven't done this in class or you haven't seen it at some point, you actually conduct these experiments if you're able to. I will sort of discuss them and their results in this video, but there's nothing like actually performing them to get a good sense of what is going on. So these experiments are under a category called electrostatics, which should remind you of sort of the static electricity. And we'll have to explain a little bit more about why electrostatics and static electricity is called what it is. But these sets of experiments led to our understanding of what is now known as electric charge. So, in experiment 1, a plastic rod rubbed with a cloth will attract little papers. So if you want to conduct this at home, you can use sort of a plastic comb of any kind, really, rub it on a shirt or a blanket. And if you take a piece of paper and tear it into tiny little pieces, you should find that if you take that plastic rod or that comb, rub it with cloth, it will attract those tiny little papers. Similarly, okay, and in the same vein, a balloon rubbed on hair. So you take a new balloon, you blow it up, tie it off, and rub it vigorously on your hair. It will stick to a wall or attract hair that is brought near it. Okay. In experiment 2, if you do the same thing with 2 plastic rods and sort of bring them together carefully, you will discover that they repel each other slightly. And in experiment 3, if you take a plastic comb rubbed with cloth and glass rubbed with silk, you will find that the plastic comb rubbed with cloth and the glass rubbed with silk will attract. Okay, and a simple setup of that kind of experiment is found here. Again, I would really encourage you to try to set this up on your own if you have not seen it in class. All right, now we, in conducting these experiments, can come to what is called a charge model. So what we're going to do is we're going to say, okay, from these results, we can explain them if we hypothesize this thing called electric charge. Now, having taken chemistry and been alive in the world, you've probably sort of been exposed to this idea of positive and negative charges, and that's where we're going. But these experiments are sort of the foundation of this model, where this idea comes from, and we'll begin to flesh it out. So we formally define this idea of electric charge given the symbol capital Q. Unfortunately, electric charge is given the symbol Q, and that is in addition to heat, which we have already seen given the capital Q. We define electric charge as the physical property of matter that causes it to feel a force when placed in an electromagnetic field. This is a formal definition, and obviously we have yet to define electromagnetic field, but that's our formal definition, something to take note of, but really what we're going to do is we're going to use the experimental results to describe what this thing called charge actually is, and what it does, how it behaves. The unit of charge is a coulomb with a capital C. Of note, is that a single coulomb of charge is just an absolutely enormous amount of charge. So often we will use milli, micro, or nano coulombs, sometimes even pico coulombs, to describe the amount of charge in a physical situation. Electric charge is a scalar and not a vector. Charge has no direction, although it is signed. So as we will see, there are positive and negative charges. You can also compare this definition, this formal definition of electric charge, to our formal definition of gravitational mass, a physical property of matter that causes it to feel a force when placed in a gravitational field. That force we refer to as the gravitational force, or when it's on an object near the surface of the Earth, we refer to that as its weight. So this is a very similar kind of thing. The analogy between charge, electric charge, and mass goes deep, and we will return to it in time. So, other things that charge has, though, that mass does not, is that there are two species of charge. Species in this use just means type. So there are two types of charge, positive and negative. And as you probably studied in middle school, like charges repel and unlike charges attract. So two positive charges will repel, two negative charges will repel. Those are like charges. And unlike charges will attract. So positive and negative charges attract each other. This repulsion and this attraction are words for sort of the directionality of a force that is produced. So charges apply forces on one another, and that electric force between the charges is long range, so it acts at a distance. Two charges don't need to be touching to affect each other, much like mass, for instance. And it depends on the quantity of charge. If you have more charge, you get a larger force. It also depends on the distance in a very particular way. So the further you are away, the smaller that force. The closer you are together, the bigger that force. So, in experiments to be discovered, in topic 7, more properties of charge were discovered. The following properties are also properties of charge, but they were not known from these original electrostatics experiments. These came to be discovered later. The first is that charge is quantized in units of the elementary charge. Quantized is a word we're going to run into a lot as we move forward in physics. Quantized just means discrete, in little chunks, or indivisible packets. It means if you take a bunch of charge and you divide it and divide it and divide it, eventually you get to a point where you cannot divide it anymore. That amount of charge, that indivisible packet, is a quanta. And the word quantized means that it's split up into these discrete countable packets of charge. And the smallest unit is what is known as the elementary charge. That's the charge, as we will discuss, on a single electron or a single proton. The electron has a charge of minus the elementary charge, and the proton has a charge of plus the elementary charge. Often we discuss charges in units of the elementary charge, which means that we describe the electron as having a charge of -1 and the proton as having a charge of +1. But if we wanted to translate that to coulombs, we would need to recognize that the electrons have a charge of -1.602 times 10 to the negative 19 coulombs, and protons have a charge of +1.602 times 10 to the negative 19 coulombs. Notice coulombs is a very big unit compared to the charge on a single electron or a single proton. And this amount of charge is known as the elementary charge, symbolized with an E. Fair warning, that E does not mean electron, although it is the same as the charge on an electron. It is also the same as the charge on the protons. You have to be a little bit careful. Sometimes this amount of charge, known as the elementary charge, is referred to as the fundamental charge. Now, one caveat here, and I know this is slightly confusing. Much later in history, we discovered that the smallest unit of charge, we think, is actually 1/3 of the elementary charge. But for now, I want you to sort of file that away in your memory, and we'll discuss it later. Okay, so in ordinary matter, protons and electrons have the same amount of charge as the elementary charge. That charge is quantized in tiny indivisible packets, and the protons are positive and the electrons are negative. Okay, good. Our next important principle to mention of charge, of our model of charge, is that charge is conserved, okay? Just like energy, and just as inviolable, that means it cannot be violated, charge can neither be created nor destroyed. The total charge of an isolated system remains constant, okay? I don't know where my word constant went, but now it's here. So charge is conserved. Charge can neither be created nor destroyed. The total charge of an isolated system remains constant. And we define the net charge, or total charge, as the magnitude of the positive charge minus the magnitude of the negative charge. So you can have a net charge of 0, Q net equals 0 coulombs. That doesn't mean that there aren't any charged particles on that object. It just means that object is neutral. That is, it has exactly the same amount of positive charge as negative charge. Most ordinary everyday objects are neutral. They have the same number of protons as electrons in the object itself.